Hello and welcome back. We have understood what is dimensionality reduction, what is curse of dimensionality, and we looked at a high level view of how principal component analysis, the PCA algorithm, helps you reduce the dimensionality with minimal information loss. Let us dive deep into PCA, the algorithm, and understand how exactly it works. The first point is that PCA is a projection learning algorithm. That means it projects our data points onto principal components and then finds out the transformed data which captures the essence of the data and which allows us to reduce the dimensionality. After applying PCA, you get a transformed columns. You pass x1, x2 and so on xn, and you get z1, z2 and zn, or z1, z2 and so on zn number of columns, out of which you can select k number of columns, z1 to zk, which will have almost all the essence of your x1 to xn, where k is less than n. If you have 1 million or maybe 100,000 columns, if you apply PCA, the PCA algorithm converts the data, transforms the data into z1 to z100 or z1 to z100,000. You can take z1 to z100 columns which will have the as strong essence as x1 till x100. In the previous slide we have seen it, right? So here if you see there are 100,000 columns. After applying PCA we have got z1 till z100. Actually what happens is it gives you z1 till z100,000, but I have chosen only 100 features which are equally capturing the essence. Whatever the strength or the information which contains in 100,000 columns is actually has got into 100 columns. That's the power of PCA. When you apply PCA, it reduces dimensionality in such a way that the total strength of your data will be captured in less number of columns. So the principal component analysis is a projection based learning algorithm which actually tries to project your data points onto principal components. This green line is principal component 1, this orange line is principal component 2. The algorithm tried to project the data, perpendicular projection onto the green line and the orange line, and then found out, it rotated the axes and then found out the z1 and z2. If you want to take, you can take only z1 which will have the essence of x1 and x2. That's how PCA works. So that is projection learning. Actually it is projecting the data points onto the principal components and trying to transform the data and find the transformed more information extracted columns. So PCA finds principal components of data and transforms our original data using the principal components. We'll see how it is in a moment. And the principal components are the directions where the data has the most variance. If you look at this green line, all the dots, right, when you look at them, they are actually strongly correlated in that direction. Correlation and covariance are same. Covariance standardized is called as correlation. Okay, covariance standardized using standard deviation of x and y or x1 and x2 are called as correlation. They are strongly correlated in this direction. So these principal components are linear combination of the input variables are x1, x2s. Here there are two features x1 and x2, and this line is a linear combination of x1 and x2. What is linear combination? Theta 1 into x1 plus theta 2 into x2. Okay, and the first principal component goes through the data, and the second principal component is going to be the perpendicular line to the first principal component. If you have third feature also, it is going to be perpendicular to first principal component and second principal component. If you have 4, then it is going to be perpendicular to first 3 principal components. It is like that. The principal component, first principal component is going to the best fit line going through the data. It's a linear combination of your input variables x1, x2 or xn. And the second principal component is also a linear combination which is perpendicular to the first principal component. The orange line is a linear combination of your x1, x2, but it is going to be perpendicular to the green line. Okay, and there is an assumption for principal component analysis. The algorithm has got an assumption. The assumption is that The direction in which x1, x2 and so on xn show the most variance are the direction that are associated with y. That means, in simple layman's terminology, if you have to say, most covariant variables or most strongly correlated variables will have most essence in predicting the y variable. The point here is, the principal component analysis will not consider y variable, only input variables it takes. Blindly it takes the input variables and thinks that the most strongly related input variables between themselves, the multicollinear columns. What is multicollinearity? More than two columns are strongly correlated, we call it as multicollinearity. The algorithm assumes that the multicollinear columns are the strongly correlated or strongly dependent columns in the input variables have got strong predictive power. And then the PCA tries to extract the correlation or covariance inside the data and tries to reduce the dimensionality. If you have 100,000 features, it thinks that there are 100 features which are strongly correlated, and those 100 features are the most important features in predicting y. Blindly assumes it. Okay, it is an assumption, right? When you apply PCA, it extracts the covariance from the dataset or correlation from the dataset and creates 100 columns. If those 100 columns have got the highest predictive power, right, you will get a good model to predict with the reduced dimensional dataset. Okay, because of this assumption, the PCA algorithm should be applied to the datasets only when you know that strongly correlated features are having the most predictive power. If you apply PCA to any dataset, right, it's not going to work. The basic reason, the basic understanding you should have while doing analysis, you should understand the most strongly correlated features have got the most predictive power or not. If most strongly correlated features have got most predictive power, then you apply PCA, reduce dimensionality, build a model, you will get as good model as built on the original data. If you have 100,000 features, built a model, you got 90% accuracy. You reduce the dimensionality to 100, and now you are trying to build a model using 100 input features, Z1, Z2 and so on, Z100 and Y variable. You will get 90% accuracy only when maybe 100 or 200 features have got strong correlation, and those 200 features are strongly related to the Y variable. The assumption is always not guaranteed. So when the algorithm has got some assumption, we need to see the data set is satisfying that assumption or not before we apply the algorithm. If the data set is satisfying the assumption, then only you should apply the algorithm. Rather, you should not apply the algorithm. This is the model selection, the algorithm selection approach. Okay, so I hope you understood. And if you have n number of features, then you will get n principal components. Generally, we select k principal components and try to multiply the k principal components with your original data to generate k z's, z1 till zk, where k is less than n. We are trying to reduce dimension. So you have n number of features, 100,000 features. You will get 100,000 principal components. But you will not take all 100,000 principal components. Maybe 100 or 200 principal components you will take and multiply your data set with these 200 principal components and get 100 columns or 200 columns. That's how you reduce the dimension. Okay. So the first principal component PC1 defines the line that is closed, as close as possible to the data. If you see this, it is like best fit line going through the origin. Okay. And then perpendicular projection of your data points onto the principal component it does, and then it takes the second principal component which is perpendicular to the first principal component, and then again it projects the data points onto those. Like that, if you have n number of features, there will be n number of principal components and n number of projections it will do, and it will rotate and find the transformed data.